Hi, welcome to this video. Today we're going to be discussing about polarization of dielectrics. We'll be covering what is polarization, what are dielectrics, what are the different types of situations such as non-polar, polar situations that are molecules, and how do they get polarized in an external electric field. So let's get started. Get your notebooks out and let's begin. Okay, so we start first of all with understanding the effect of electric field on first a conductor. Now what happens in a conductor when there is an external electric field? Suppose this is a piece of conductor, okay, it can be a piece of any metal, iron, aluminum, whatever, okay, and there is an electric field like this. This is the external electric field in which this metal piece is put in. What happens is the free electrons in the conductor, keep on start moving in the direction opposite to the electric field. Why? Because the electric field works opposite, it attracts. So if an electron is here, it will move this way. If an electron is here, it will move this way, right? So the free electrons start moving and they align themselves in such a way that the negative charge comes here. There is a concentration of negative charge here, and on this side there is a concentration of positive charge on the surface of the conductor, right? Now as soon as this happens, you can now see from positive to negative there is another electric field that will be created, which is inside the conductor. In this static situation, there will be an internal electric field which gets created from this side, which is the positive end, to the negative side, and this is actually equal to the external field. So if external field is E, the internal field is also E in the case of a conductor. Okay, this is a basic fundamental property of a conductor, and this is in a way a differentiating factor between conductors and non-conductors. So when we see a piece of material which we do not know if it's a conductor or not, and we see this property happening in it, then we say that yes, this piece of material is a conductor, right? So what is happening is this external field is getting cancelled out by the internal field produced in the conductor due to the shifting of electrons and charges on its surface. This is a very important point. So this is what happens in the case of a conductor. Now what if we talk about a dielectric? Let's first understand what a dielectric is. A dielectric are materials. Dielectrics are materials which are non-conductors. That means they do not have free charged particles like electrons that can move from here to there in their body, right? So dielectrics are materials which which do not have free charge particles which can move around easily. So they do not have electrons, and then they do not create an internal electric field exactly as the same as conductors. But what they do have is their molecules gets stretched. Their molecules gets stretched due to the external electric field. The molecules get stretched due to the external electric field, and due to this stretch, what happens now is you can see that the alignment is also happening. The positive charge is towards this, the electric field direction, the negative charge is this way. What happens is there is a partial charge that is created on the surface, which in turn produces an electric field, an internal electric field inside the dielectric as well. Okay, it produces an internal electric field inside the dielectric as well. So dielectrics are materials which do not have free electrons to move around, but when put in an external electric field, it gets stretched. The molecules of the dielectric get stretched, and because of that stretch, there is a dipole moment that gets created. Due to this dipole moment, there is a partial charge on both the ends of the surfaces of the dielectric, creating an internal electric field, but not as strong and not as equal to the external electric field. We'll get to that towards the end of our conversation here, but this is what the basic scenario and the concept is, right? So now let's first understand what are the properties of dielectric, and especially what type of dielectrics are there. So dielectrics have two types of molecules. One is polar and second is non-polar. Now, as the name suggests, polar means they can get polarized. Non-polar means they can't easily get polarized. Okay, they also get polarized but not easily. So polar also means that they have an intrinsic dipole moment. Let me explain with a diagram. When I create this molecule, so this is a molecule of H2O, which is water, where O is pulling the electrons. There are shared electrons between O and H on both the sides, but the O, because it is powerful, it is more powerful, it is pulling the electrons towards itself, creating a partial negative charge over here and a partial positive charge over here, right? When this happens, when there is a partial negative charge, partial positive charge in an overall neutral thing, we say a dipole moment, a permanent dipole moment is being formed. We're not getting into the detail why oxygen pulls the electrons towards itself. That's a concept that you'll study in chemistry, but what happens is oxygen does pull the electron towards it, and due to that pull, it creates a partial negative charge and a partial positive charge permanently in the molecule, creating and giving it a permanent dipole moment. So polar molecules are molecules which have permanent dipole moment, okay, which have permanent dipole moment. With what does this mean? This means that when I put this molecule in an external electric field, the positive charge end will automatically get attracted and get aligned towards the electric field. Okay, the positive end will automatically get aligned and attracted towards the positive end. That is the importance here. What are the other examples of this? HCl, okay, which is a very common acid. Again, Cl being the more powerful of the two, pulls the electrons towards itself, creating a partial negative and a partial positive charge on the molecules, on the parts of the molecules. Okay, so this is about polar molecules. Okay, we are talking about the molecule structures over here right now. Now, what about non-polar? What are these? Non-polar molecules are essentially molecules like HH or OO. OO is essentially O2. This is H2. Okay, hydrogen gas, oxygen gas. Now here, due to symmetry, none of the atoms pull the electrons towards itself, and so both of them have equal strength. When they have equal strength, they are neutral as a whole. That means there is no partial charge on top of them. right? What this means is there is no permanent dipole. But if there's no permanent dipole, then why are we talking about it? We're talking about it because even though there is no permanent dipole, in an external electric field, these molecules also can get stretched. Okay, so we'll come to that in the next segment. So these are the two types of dielectrics that we'll be discussing. Let's first discuss what happens to non-polar molecules in an external electric field, and that is what we'll cover in this video. In the next part of this, we'll cover the polar molecules and the rest of the dielectric polarization. Now, non-polar molecules, how do they behave? Imagine a non-polar molecule like this. What is happening? The centers of the positive and the negative charge are overlapping, creating a neutral molecule, right? So creating a neutral molecule. This is my material and these are the molecules in it when there is no electric field, external electric field. Now, when I put the same material in an external electric field, what happens is the external field starts pulling the positive side this way and the negative side goes the opposite way, and so it gets stretched. It gets stretched and so on. As you can see, when something gets stretched, it elongates. When it elongates, the center of positive and negative charges are not overlapping. When they are not overlapping, it becomes an induced. It gets an induced dipole moment. It gets an induced dipole moment. Induced by what? By the external electric field. Okay. Now, for the sake of simplicity here, we are only talking about cases where the dipole moments are in the direction of the electric field. Of course, the dipole moment can be this way as well, that is in a slanted direction, but obviously that is a little bit more complex at the stage that we are at. So right now we are only talking about the dipole moments which are in the direction of the electric field. So those kind of cases are called linear isotropic dielectrics, and what happens in this is essentially the dipole moment that is induced, the dipole moment that is induced is directly proportional to the electric field put outside. Okay, the electric field put outside. So that is what we are discussing over here, right? So this is what happens in non-polar molecules. Now, when there is a dipole moment that is induced, obviously the charges are not that much, right? So, but there is, because the charges have separated, you can now see that there will be an electric field in the opposite direction to the external electric field. There will be an electric field which is opposite to the direction of the external electric field. Why? Because from this positive end to this negative end there will be an internal electric field. Okay, but it is obviously not as strong and it's not equal to the external electric field. So in non-polar molecules there is an induced internal electric field opposing the external electric field, and that is the most important point. Okay, so this is it for this video. and I'll talk about the polar molecules in the next part. Do watch it. Thank you for watching this video. If you did like this video, do subscribe and share and comment on this video so that more and more people can get to know about this and get clarity on their thinking about physics concepts. If you've liked this part, then do watch the second part because it is in continuation to this, and I'll see you in the next video.